All right, so we're going to now look at balancing redox reactions via the half-redox method. This is a different approach that accomplishes the same task as before. The first method I showed you was the direct method. This is now the half-redox method. And some people love this method, some people hate this method. The same thing goes for the direct method. So here is going to be where you get to choose which way you want to approach the problem. But let me show you how the half-redox method goes, and then you make the decision as to whether you like it or not. All right, so what you do in the half-redox method is to first break the equation into two halves. One half has to contain the same two elements, the same two non-oxygen, non-hydrogen elements within it. The other equation will have to contain the other non-oxygen, non-hydrogen element within it. And then what we're going to do is completely avoid the idea of looking at the individual charges or even using the charges to come up with electrons for the, based on the individual atoms. We are going to literally balance the oxygens um, and the hydrogens first and worry about the electrons last. So let me show you how this plays out. We have the same equation, dichromate plus vanadium leading to chromium 3 plus and vanadiol. So I'm going to split this up into the two half-redox reactions. One that only contains chromium and the other one that only contains the vanadium components. All right, so here we go. This is the same equation. The dichromate and vanadium are still on the reactant side, but now they're in separate equations. And the chromium 3 plus and vanadiol are still on the product side, but they're on separate equations. Notice that chromium remains with chromium, vanadium remains with vanadium. All right, now what we're going to do is we balance the non-oxygen, non-hydrogen atoms like we did before. That means that chromium, which we have two of on the reactant side, needs to be balanced on the product side by adding a 2. Vanadium, we have 1 and 1 on each side, so that's taken care of. Now here's where the process differs. We don't look at the charges, we don't even look at the electrons. Instead, what we do is we go ahead and start balancing the oxygens. We have 7 oxygens on the left side of the first equation, none on the right side, so we're going to add 7 waters to balance it. Here for the vanadium equation, we have 2 oxygens on the product side, none on the reactant side, so we're going to add 2 waters on the reactant side to balance it. Alright, and so we go straight for balancing the oxygen. Now what we need to do is balance the hydrogens. We have 14 hydrogens on the product side, none on the left side, so we need to add 14 H pluses. Okay. We have 4 hydrogens on the reactant side, none on the product side, so we need to add 4 H pluses on the product side. Okay, so we've basically gone directly into balancing oxygen and hydrogen in both of these half-redox equations. It's at this point that we now look at the electrons. Now the way we're going to do this is by looking at the collective charges on the product and reactant sides alike. I'm going to make a little bit of room so that you can see what that is in terms of the numbers. Alright, so now looking at dichromate. There's only one dichromate and it has a charge of 2 minus. There is H plus, but there's 14 of those. So we have 2 minus plus 14, leading to a charge of 12, overall charge of 12 on the reactant side of the first equation. On the product side, we have chromium 3 plus, 2 of them, multiplied together gives us a charge of plus 6. Water is neutral, so it doesn't contribute. Down here, water and vanadium are both neutral, so the overall charge is neutral. And on the product side, we have vanadiol with a plus 1 charge, only 1, so 1 times plus 1. And we have H plus 4 of them, so 4 times plus 1, added together to give us an overall charge of plus 5. Okay, so the way this works out is we pretty much subtract the difference. We have 12 minus 6, and we have 5 minus 0, we have 5 and 6 electrons that we are missing. Now, pretty much all you're trying to do is take the number of electrons and add them to the side that has the highest charge. The highest charge for the first equation is 12, right? 12 and 6, 12 is higher, so you're going to add 6 electrons to that side. Over here, you have 0 versus 5. 5 is the higher charge, so you're going to add the 5 electrons to the right side of the equation. Okay. And the idea is that yes, the electrons go wherever the charge is highest, but it has to be based on the charge difference of both sides of the equation. Okay. All right, now this is the part of the half-redox method that some of you are gonna absolutely hate, and it's the fact that we now have a balanced half-redox reaction for each of the redox reactions, but we still want to come up with an overall balanced equation. So we're gonna have to balance the electrons, and that means that we're going to end up with a lot of high numbers for both the equations. So here we go. Let me clean this up a little bit. We have 6 electrons on top, we have 5 electrons on the bottom. We need to multiply the entire top equation by 5. And also, we need to multiply the entire bottom equation by 6 in order to balance the electrons. So here we go. That entire equation gets multiplied by 5. This entire equation gets multiplied by 6. That means that we will end up with 5 dichromates. 5 times 14, which is 70 H pluses. 5 times 6, which is 30 electrons. 5 times 2, which is 10 chromium 3 pluses. And 5 times 7, which is 35 waters. Alright, so we get that entire business there. And we do the same thing for the bottom equation. We multiply everything by 6. So now we end up with 12 waters, 6 vanadiums, 6 vanadiols, 24 H pluses, 30 electrons. The electrons have been balanced. What we do now is we bring the equations together. We literally add them up. And anything that is present on both the left side and the right side of the equations have to be cancelled out, or at the very least, cancel out such that you only end up with the component on only one side of the equation. So case in point, 30 electrons on the left side and 30 electrons on the product side fully cancel out. But looking at this, we have 35 waters on the product side and 12 waters on the left side of the equation. So that means that we're going to partially cancel out the waters. All 12 waters on the left side of the second equation go away. But you subtract 12 from 35 to come up with 23 waters. The same thing goes for the H pluses. You subtract all 24 H pluses from the product side. You subtract 24 from 70 to get 46. And at this point, you write down everything that you have. And that is 5 dichromates, 46 H pluses, and 6 vanadiums on the left side of the equation. 10 chromium 3 pluses, 6 vanadiols, and 23 waters on the product side of the equation. And this is the complete balanced equation. You can look at the charges to make sure that this has all the proper formats. But if you add up the charges on the left side of the equation and the charges on the product side of the equation, you'll find out that the charges are balanced. So this is how to balance a redox reaction using the half-redox method.